this will complete today. Then some starter on bias variance trade-off, overfitting, underfitting models. Then that will be kind of the pretty much end of your basic machine learning things. Next, there will be a series of guest talks and maybe 3 more class on basic machine learning before ends. Okay. So yeah, so as yesterday I mentioned, this today's class will be a part of quiz also. So be attentive. So before going to decision tree, so just a quick uh, kind of overview of like different types of machine learning models. So we discussed generative, discriminative, those kind of models. But there is two more classification we can do for ML models. That is linear and nonlinear. Linear models and nonlinear models. So like a few things I'll be doing on the board. So they're not on the slides. I'll update the slides and share to name. Okay. So what is linear model and what is nonlinear model? So we studied linear regression. We studied logistic regression. You have seen perceptron, multi-layer perceptron, all those things, right? So when we say some model is linear model and when we say some model is nonlinear model, so this linearity or nonlinearity comes from the relationship between a relation between input x and the corresponding feature w. So if the input x and the corresponding feature w is linearly related, then we say that model is linear model. Let's say one example is, let's say w transpose x, we say w transpose x, it is linearly related, w is linearly related to x. So if a modeling follows this kind of formulation, then it is a linear model. But let's say logistic regression, we know what is logistic regression doing. So for like what is our f theta x in logistic regression, it is 1 by 1 plus e to the power minus w transpose x, right? So here w transpose x is there, but it's exponential of that, like it's not linear relation between w and x. So whatever x has input given to us, so there is an exponential term that we're multiplying. So if you break it, this is minus w transpose e to the minus x, right? Sorry, yeah. No, not like this. This is wrong. So, but you can assume, so x, the x and the corresponding parameters are not linearly related here. So let's say I will say another f theta. Let's say that is w transpose x w. So here, this is also not linearly related, right? So it's like x and w has like quadratic relation. So if such kind of formulation happens, so we say that they are nonlinear models. And if the relation between w and x is kind of completely linear, there is no non-linearity between the relation between w and x, that is linear model. So that's the major classification for linear and nonlinear. So there is one question on quiz based on this concept. So I thought keep better cover before starting decision tree. So what all the models we have discussed, like linear regression that relies on this, that is linear model. Logistic regression, even if it is classifier, it's a linear classifier, but the relation between w and x is not linear. So we don't say this as a linear model. This is non-linear model. So in like kind of neural networks, so what happens? So you have input features x1, x2, x3 up to xn, right? Input features. Then you have like perceptrons, right? One layer perceptron or multi-layer perceptron. Then you make decision. That relation between w and x, these are w's. Layer 1 w, layer 2 w. Then this is output layer, let's say. So this relation, whatever the w are multiplying with x, w1 transpose whatever the x vector, whatever x vector, if I am representing like this, if this is directly multiplied like this, then this is linear, right? But if I say this is sigmoid of this, the whatever the output of each neuron, like it's taking double transpose x, then doing sigmoid operation, then doing the output, then this is called nonlinear. So if you add sigmoid to every neuron, then it becomes nonlinear, right? So this is the distinction between linear models and nonlinear models. Okay, so now let's get into the decision tree. Then we'll end with bias variance trade-off. So in decision tree, so what is the setup? You have a so any doubt on linear non-linear models? So when we say something is linear, something is non-linear in terms of ML models. Okay. So in the decision tree, what is our task? Like you are given some data set. So data set have some input features, some Y label. So in this scenario, whatever the example we have taken, so the theory of decision tree generally is taught with examples. It's not very much theoretical. It's kind of applied thing. Um, so if you consider this is a given example, which have like features like pitch type, host, and which country batted first and who is the winner. So this is our Y level, right? So let's say we're trying to predict the probability of India winning the match. Then we'll check what is the probability of what is the probability of Y equal to India here, right? So this is what we'll check. So this is our Y level. So what's the goal? How like which combination of these features? This is feature one, feature two, feature three. So which combination of this feature will give us the like correct prediction? Okay, we know okay if pitch type is screen friendly, host is India, then irrespective of who bats first, India wins. Let's say this is what we understood. So this is kind of the analysis we want to know from the given data set. So that's what decision will help us. Right. So what's the task? Make decision to predict if India can beat Australia in upcoming match, whatever it is. So something called how do we do? We'll use information gain or gain ratio or Gini index to kind of build decision tree and decide that. What are these information gain ratio, Gini index? We'll see next. So before to understand Gini index, we don't need any prior, but to understand information gain, we need to know something called entropy, right? So you might know, but I'm just covering as part like for completeness. So what is entropy? Entropy kind of a vague definition of entropy is randomness. If some model is very random, we say the entropy of that model is very high, or some probability distribution is given to us, let's say like uniform distribution, it is completely random, then we say the entropy of the uniform distribution is high. But let's see that why it is high, right? So let's start with some random variable x that is sampled from Bernoulli with probability p. So how do we write? Probability if for x equal to 1 is p and probability of x equal to 0 is 1 by p, so 1 minus p. So this we have discussed already. So what's the formula of entropy? The formula of entropy is this actually. So if x is kind of taken from the distribution of px, so entropy says like what's the log likelihood kind of negative log likelihood of the each probability term, right? But we cannot we don't know the true distribution, as we have already discussed. We don't know the true distribution. We always compute whatever the probabilities from the sample distribution. So if you kind of come back to our sample distribution, how do we write? Let's say whatever k classes we have. So we say what is the probability of x, like one particular instance belonging to class I, and then this is kind of the expectation formula, right? So if you open this expectation, this will come like this: probability of x equal to I and learn to log probability of x equal to I. Right. So if it is continuous random variable, you do the integration. Now we need to know because by definition entropy is randomness. So we want to know which probability for Bernoulli random variable, which particular probability will give us the highest entropy. For that, what we do? We perform the MLE. So we have already studied MLE kind of helps in this kind of setup. So we'll do if you do MLE. So what we have to do? You take the kind of Jacobian or the first derivative, you equate it to zero, and Hessian or the second derivative, you say it is like less than zero. Like whatever the Hessian you are computing, that is less than equal to zero, right? So first derivative, if you compute, it's minus. We know this is minus log p, one minus p, log one minus p. So if you compute derivative with p, it will be minus p by p. Then log p will stay p by derivative with p with respect to p will be 1. Then the second term will be similarly plus, actually minus log 1 minus p. So that will convert into plus. So now what's our target? We have to equate it to 0. So whatever this del h by del p we got, that we have to equate it to 0. So this is not correct. So this has to be del h by del p equated to 0. So if you equate it to 0, okay, so this is not updated. So then you will get this formulation and you will get P equal to half. So this is for the Bernoulli. You got, okay, if P equal to half, we have the maximum randomness or the maximum entropy, right? So what is that maximum value? So the maximum value will be, if now we have to put the whatever the optimized P you got in this formulation. If you put that particular value, we'll get log 2. So how the kind of the distribution of entropy will look for the Bernoulli random variable. So for that we need to know. So we know at 0.1/2 it will be log 2, right? So whatever if this is y-axis, this, let's say this is log 2. This is what we know, right? So let's see what will the value at if p equal to 0 and p equal to 1. So what will be value if p equal to 0? So you take limit p tends to 0, and because we want to see what's the nearest point on like for p we want to work like taking care of, it's p towards half, right? So that's why I've taken 0 plus. For 1 it is 1 minus, right? So all these limiting limit terms you know. So if you take limit p tends to 0 plus, so you can solve this. You will get a limit of whatever the term we got this term with the p tends to 0 plus, it will be 0. Similarly for 1 minus, it will be 0, right? The curve will look like this, right? So what it says, like for Bernoulli random variable, if your probability p value is tends to 0, or meaning if your probability p values are tends to 0 or 1, uh, what's the entropy value? Entropy value is least, right? Why it is least? Because you are very sure either it is 0 or 1. It's a like surety event, right? The event, you know, okay, it is happening or not happening. So that's why the entropy is least. But if p is half, so it's like one event can happen or other event can happen with 50% probability. That's why the entropy is highest here. Sorry, some miss have happened. Okay. Um, yeah. So that's the entropy term. Now we'll see how do we apply this entropy term into this discussion on information gain, right? So before going to again the information gain, so what do we do exactly on yeah, while using decision tree? So some data is given to us. Some features are there in the data, right? Some features are there. Y1, F1, F2, F3. Some features with some Y level. So you want to get so when a particular Y class or Y level will happen based on some combination of F1, F2, F3. So you will create a decision tree. So the decision will happen based on these features, right? So you will create a tree based on these features, whether root node will be feature 1, whether it will be feature 2 or something. Then you split based on feature 1. When feature 1 happens with some particular value, what is the value of Y? Based on that, you split the tree. So that we'll see with one example. So what you do in generally decision tree, decide which feature to split on. So how do you decide? So you decide based on something called purity, right? So we'll see what how we'll compute purity and what is purity. Then split point, what particular value for a particular feature you'll get where you will split, and when to stop the splitting, right? So these are the three major decisions we have to make while constructing the decision tree. Once we have constructed the decision tree during test time, what happens? We know the features of the given input instance, right? Test instance, and we know which feature we are splitting on first, right? Given the input instance, we take the whatever the corresponding feature on the of the root node, whatever the splitting point we know for that particular feature. Okay, this feature is greater than 0.5, then we'll come to left side or we'll come to right side. That we know how do we traverse, and when we stop the splitting, we'll see what is the corresponding Y level, right? So what is purity? Purity is how homogeneous a node is. If a node is homogeneous, so what do you mean by homogeneous? Let's say feature 1 has two value, 1 0, and so Y has also two value, but for particular this feature taking 1 or 0 value, Y is both 1, right? So we don't get any particular information from feature 1 to decide Y equal to 1, right? So for Y equal to 1, for y equal to 1, feature 1 is homogeneous, right? So this is what we mean by homogeneous. When we say heterogeneous, let's say let's say I am writing y prime, f1 is 1 0, y prime is also 1 0 or 0 1, whatever it's in other way also. Then we know for particular f1 value there is a particular y prime value, right? So there's this is, so y prime, we can say for y prime f1 is heterogeneous, right? So that's what the purity gives us, if it is homogeneous or heterogeneous. Then a goal is to split to create a child node that are purer than the parent node, right? So then so which is more pure here? So if y prime is 1 0, then f1 is more purer than the scenario if y is 1 1, right? So if we have y prime, then we can split on f1. If we have y, there is no point to split on f1. We will not get any information, right? Then we'll continue till we have a single instance class. So this we'll see next. So what are these for computing this purity? What are the general functions? So I have mentioned I will be discussing 3 functions, but there are many more functions available depending on the data set type. We can explore. One is Gini impurity, one is information gain that relies on entropy. So the example we will do is based on the entropy, but in quizzes or exams you might ask you might expect questions on Gini impurity or whatever the variance reduction, right? So there are not much difference, just the formula is different, nothing else. So if you see Gini impurity, what it tells, so you have to compute something called Gini index for a particular node. Gini index, Gini index for a particular node. So how do we compute the Gini index? When I will go through the example, I will tell you. So again, for information gain, so for a particular node, and again for a particular node, what is changing, for a node compute information gain. So let's say we have, so what is a node for us? For us, the node is each different features that is given to us, right? So we will assume that we're having the root as speech type, or root node as speech type, whether the root node as host or whether the root node as batting first. Then assuming each of them are root node, we'll compute the information gain of each of the root node. Whichever root node has the highest information gain, we'll decide that as the root node, and based on that we'll conditioning on that root node, we'll again decide where is the splitting point, when we'll go to the left, when we'll go to the right. And once we have decided that, then at this level again we'll decide what can be the node at this level. Node can be based on again feature 1 or feature 2, that will again based on what is the information gain at layer 2, right? So each layer will compute the information gain and decide which feature to split on and what will be the value of the splitting point, right? All these things we'll see again with the examples. So so the example I have taken, I have shown you, this is for the classification, but this decision tree can be the decision tree can be applied for the regression also. So this is a very simple scenario we have taken. All the features are kind of categorical features, not kind of continuous features, and this is a classification scenario. So decision tree can be applied to like kind of continuous features with like kind of when we're regressing some output values, or continuous feature when we're doing some classification. So those things I will give you high level overview, so you can explore on your own. Right. So, like for a regression task, so how do you decide what will be the root node and what will be the node at the layer 1? On based on which feature you compute the variance. So, what will the how do you compute the variance? Let's say you like kind of split the data point into 2 subclasses. So, what happens in the when you split? So, you decided to split on a particular feature f1, right? So, what is the splitting point? Let's say f1 whether less than equal to 5 or not. If it is less than equal to 5, you come to left side. Whether it is greater than, if it is greater than equal to 5, you go to the right side. Based on this feature f1 less than 5, your data set will be, let's say 60% of the data points will come here, 40% of the data point will come here. You are splitting the data points and kind of supplying it to like kind of the leaf nodes, not leaf nodes, nodes at the layer 1 If it is the leaf node, or it's leaf node, or otherwise its nodes are layer I, right? So based on this 60% data point, so you compute the variance. So whatever your predicted yi and sorry, whatever is the ground truth yi, whatever is the predicted y, and take the mean of that, you compute the variance. Right. So again, how do you decide to split? You compute the variance beforehand, and then if you are splitting on the feature one, if you take decision on the feature one, what will be your predicted y, and what will be your ground truth y? You compute the variance. If the variance is kind of highest, then you split. Right. So that's the pure split. Right, so that's our splitting strategy based at every layer of the tree. So you decide which feature to split. How do you decide? You compute the purity of each feature at that particular layer. If the purity is high, in a way, if your information gain is high, then you split on that. So let's take this example and discuss in detail. So the purity, information gain, where to split, where to stop, all these things will be clear now. Right, so just keep this example in your mind. I'll coming back and forth to this example also. So what we have to do initially, we have to compute entropy of the whatever the y level, right? So this is our y level. You have to compute entropy of that. So what is the entropy of this? So when I say y level, our original task, if you remember, to check the probability if India wins, the next match, right? So that is our probability we want to check. If you like kind of, if this is our random variable, then that random variable takes 1 here, 0 here, 1 here, 0 here, all these things you know, right? Now we will compute the kind of entropy of this particular prediction, like to be predicted y column, using the whatever the random variable we have, right? So how many total matches we have? We have total matches. How many times India wins? 5 times India wins. 1, 2, 3, 4, 5. 5 times Australia wins. Then what will be the entropy of that y level from the given data? So entropy, we know probability. This formula we already know. Summation of probability I into log probability of I. Right. So you put these values. So there are two classes. Either India wins or the Australia wins. For India wins, the probability is 0.5 or half, or Australia wins also 0.5 or half. If you put the values and take log base 2, what's the entropy you will get? Entropy from the given data of the y level is 1, right? So that's the first thing you have to compute, the entropy of the y level from the given data. Right now, so we have not constructed the tree now. So we have just computed the entropy of the given y level to us. Now we have to decide which feature to split on. So which feature we have to split on, which the feature that will give us highest information to predict y. So how do we decide? So we'll compute the entropy of each. Let's say I'm starting with pitch type. So pitch type has how many categories? One is spin friendly, one is space friendly, one is balanced, right? So you compute the entropy of each of each category, each type in the category pitch type, right? So what will be the entropy of spin? So just bear with me. Let me complete this example. It will be very clear, right? So out of all the matches happen on the spin friendly pitches, so there are 1, 2, 3, 4. Out of these 4 matches, how many times India won? India won once, twice, thrice. 3 by 4 times India wins. So that is the conditional probability of India winning given a spin friendly pitch. So that's the kind of that's the conditional probability. So this is just P India written here. This is actually probability of India condition on spin friendly pitch, right? So that is 3 by 4 us. Similarly for Australia it is 1 by 4. Now what we'll do? Now we'll compute the entropy of the spin friendly pitch. So again, this is written entropy here, but it is actually entropy of spin friendly pitch. So yeah, so um, entropy of whatever the y level given spin friendly pitch. So what it tells us, like how random will be our y level if we know we are given a spin friendly pitch, right? If it is very random, we will not split on that. We will not split. Like if then we'll collectively decide on the pitch type. This is for just the one category of the pitch type, right? So again, this is the simple entropy computation, pi log pi, summation of minus pi log pi. So I've done the calculation. You can check later. So this is 0.81. Right, for the spin friendly pitch. Again, for the pace friendly pitch, you have to see how many times pace friendly pitch was there. 4 times, I think. 1, 2, 3, and out of that Australia won every time, right? So then what will be the entropy? India, again, this is conditional probability. India winning given pace friendly pitch, Australia winning given pace friendly pitch. This is 0, 1. Then entropy of pace friendly pitch will be 0, right? So if you put all the values, you will get 0 here. Right, now coming to balance pitch. So out of three scenarios when matches were happening on the balance pitch, then India won twice and Australia won once. The entropy of that particular feature is 0.91. Now what we do? So we compute the something called weighted entropy of this particular feature or whatever the feature pitch type was there. How do we compute the weighted entropy? Weighted entropy is how many times, like the probability of one particular pitch type and what is the entropy of that pitch type. Right. So again, this is for the pace and the entropy of pace and probability of balance, entropy of the balance, right? So if you see, so you are getting weighted entropy of pitch type is 0.5998. So what does this say? This is the entropy of y given pitch type. If we know pitch type, so what is the entropy of knowing whether India will win the match or not? Right, so give if we didn't have any conditioning, just we know the y levels, what was the entropy of that y level? It was 1, right? Now we know if pitch type is given to us, what is the entropy? So the entropy is 0.59. So what is the information gain? Just the difference between that, right? When conditioning was not given and when conditioning is given. So that's the information gain for that particular feature pitch type. Similarly, you will compute the information gain for the second feature host. You will compute this information gain for the third feature batting first. So I have computed it. You can check on your own later. The information gains are very small, 0.029, and for the second third feature also 0.029. Now you have to decide what will be the root node. So you know the information gain for the pitch type is highest. You start with the pitch type, right? So here it's a categorical feature, so that's why it is easy for you to make decision. Okay, so now how do we make the decision? So there are three categories, right? One is spin, then one is pace, one is balanced, right? So you split on that. Now data set will be like kind of divided accordingly. When match was happening on spin or pace or balance pitch, here we know entropy is 0. So once entropy is 0, so there are this is one of the stopping criteria. If entropy of one particular node is 0, then you don't explore this node further, because what do we mean by entropy 0? Given pace friendly pitch, we can blindly say who will win the match from the given data, right? So that we know Australia will win the match. So we don't explore this node further. Now here the entropy were non-zero, right? Now we'll decide based on two more features. Like already on the pitch type we have splitted. So already pitch type we have already splitted. So in the second layer we are not allowed to use pitch type any further. So we'll check conditioning on the pitch type, whatever like subsample of the data we have, we'll again compute the entropy of host here or kind of batting here. Similarly for this, you will compute the entropy of host, then batting. You will again see which node has completely zero entropy, then you will stop. If node doesn't have completely zero entropy, then you will further explore based on the remaining feature. So now you have done based on pitch, you have done based on, let's say, batting, then only remaining feature is host, right? So there is no second feature, only based on host, right? So when now how will stop? You have exhausted all the features, so you have reached here. This is a leaf node. You don't have any other features. You stop your analysis there, right? So this so I have not completed this tree construction for this example. You can try on your own at home. So I have just given you at layer 1 what will happen. So you extend with for the layer 2. right? So what are the stopping criteria? Stopping criteria is pure. So first thing is no significant edge. Like if you are getting, so we decided based on the information gain of each feature, right? So you compare all the three features, you are not getting any significant information gain, or you are getting equal information gain, right? So for all feature you are getting equal information gain or not significant information gain. So what do we mean by significant information gain? So by design, so when I'll discuss now the concept of underfitting, overfitting, I'll come to this point again. So uh, you can say we can split always if you have information gain is non-zero or greater than zero, right? But if you do that, what happens generally? You are just overfitting the data, right? So what do you mean by overfitting the data? I'll come here. So generally, this is a design choice. You can have some delta value here. Okay, I'll only split if the information gain is at least delta, right? So that will get like help us to get rid of this overfitting scenario. Similarly, for to handle those kind of again overfitting scenario, we can use another regularization feature, that is like what is the minimum sample that after splitting, now we have, let's say here 4 samples, here 5 samples, here 4 samples. I'm just giving you examples. I don't know what will be the exact numbers. So you have some criteria. Okay, if the minimum number of sample is 4, then only I'll split. I'll make some decision. Otherwise, I will not make decision. So let's say here it is 3. So for this particular node, I'll stop. I'll not explore further because the minimum sample criteria doesn't satisfy. So this also helps to kind of get rid of this overfitting scenario. Again, similarly, maximum tree depth. So this is depth 1, this is depth 2, like this. So that also helps to get rid of overfitting. And no feature to split, it's a very basic scenario. Now coming to pure node. So again, this is 1, 2. Yeah, pardon. So if leaf node is not a pure node, we know it's not classifiable now. So we'll stop there. So whatever, so here we are not making any decisions based on this leaf node further. So we'll say here entropy is highest. If we're reaching, let's say we started with pitch, then we came to batting, then we came to post, we cannot make any concrete decision. That's the output we'll give. It's a probability of India winning is half, Australia winning is half. Right? It's not always we'll make some decision. If this is the one scenario, if leaf node is not pure, you randomly make some decision.